Yeah, so my project is about optimizing the use of sugarcane mill byproducts. And so my kind of introduction to enhanced weathering and involvement has been trying to kind of assess whether we can use sugarcane mill ash as a feedstock for enhanced weathering. And I've ended up doing a lot of modelling in this area as well because of that. So today I'm going to talk about some fairly preliminary results from some recent modelling work that I've done, trying to understand mechanisms and soil properties that drive CDR by enhanced weathering. So a lot of the work that's been done, especially in terms of geochemical modelling, has been looking at and assessing the impact of the properties of the feedstock and the materials themselves. And then less well studied in these geochemical models is the impact of climate and soil properties. And this really should be better represented as a very wide variety of very complicated parameters that represent soil and climate compared to a fairly small subset of properties of the materials. And actually all of these properties interact in lots of quite complicated ways. And so it's quite a big knowledge gap about how these things all come together to affect CDR. And kind of one of the clear examples of these interacting climate and soil factors is the relationship between annual rainfall and soil pH. And so you can see here on this map that most of the soils in the global tropics where we have high rainfall are strongly acidic. And so what does that mean for CDR? Well, we know that high rainfall is good for CDR because you get more of that weathering reaction happening, but low pH is bad for CDR because we get more of that strong acid weathering and less of the weathering by carbonic acid. But both of these conditions are typically found in the same location. So it begs the question, what actually naturally occurring conditions are optimal for CDR, not just those that we can make happen in a model, and how do we untangle all of these interactions? And so the aims of this modelling project were to determine the optimum soil pH for CDR and to investigate how and why other soil properties influence the relationship between CDR and soil pH. And our approach with this was to run experiments using a reactive transport model, and that was done in the geochemical modelling software called Freak. The model started as the model published by Calland et al. In 2020, but we've made quite a lot of changes to the model since then that I'll go through soon. But essentially we used data from published field studies to set up virtual soil profile that we could then manipulate for our different experiments. So this is just a visual representation of our kind of virtual soil profile. It's just code in reality, but to try to visualize it, we have this soil profile and the model kind of alternates between transport steps where it moves the soil solution down the profile, and then it alternates between an equilibration step where the soil solution reacts with the environment. And that represents hundreds of geochemical reactions, which is essentially what the soil is, this big sum of lots of geochemical reactions. So in terms of the changes that we've made to the model that make this work kind of new and unique, we've included nitrification reactions and addition of annual nitrogen fertilizer, which we know is important for including strong acid weathering. We've also linked soil properties with climate conditions like we see in the field, so pH, solution and exchange chemistry, soil mineralogy, and infiltration and evapotranspiration. We've also modelled mechanistic pH buffering, so using exchange site chemistry on organic matter and oxides and clays. And so all soils have some capacity to resist changes in pH, either by absorbing or releasing acidity. And so we've included that in our model. And we've also had various properties change with depth over our profile, including CO2 production and loss, plant uptake of water and nutrients, our organic matter exchange sites, and incorporation of the material. And our final main development is that we've had the soils run for a 20-year spin-up to equilibrate before we've run our experiments. And so as you can see in this diagram here, in the first year, 5 years, our pH is increasing, and it will be initially unstable and just keep increasing on its own before we've even added any amendments. And after 15, 20 years, our pH starts to stabilize, and we've got a kind of stable soil that we can then start to manipulate. So in terms of our experiments, all of our experiments have 3 materials applied: 50 tonnes per hectare of our local basanite, a local sugarcane mill ash, limestone, and we've got control profiles as well. And we're testing 5 different pHs for the soil. And then in this experiment, we're comparing the impact of having a constant or a varied climate. And so by that, I mean, so in our constant climate, we've varied the pH, but we've kept our climate parameters at a moderate level, and all of our soil chemistry is the same except for pH. Where in our varied climate, we've changed our rainfall and evapotranspiration and our other soil chemical properties so that they match a more realistic field scenario. So high rainfall in low pH scenarios and low rainfall in high pH scenarios. And so this first result shows you the 3 different materials in our 3 different colors. Soil pH at the start of the experiment across the x-axis, and our cumulative CDR in tonnes per hectare on the y-axis. And that's the cumulative CDR after all of the material has effectively weathered. And so in this unrealistic constant climate scenario, we see a CDR just increase linearly with pH. And however, when we model climate and soil properties more realistically to what we see in the field, that relationship changes very dramatically, where we have now an optimum at around 6.5 and pretty much negligible CDR in our most acidic and most basic soils. So in our future experiments, we keep running with that more realistic varied climate. But in this experiment, we're changing the scenarios. So we have a high and a low pH buffering capacity and a high and a low carbon dioxide concentration in the soil to have a look at the effects of those. And so this first result is essentially comparing the 2 carbon dioxide concentrations of the soil. So as we would expect to see, we've got higher CDR where we have higher CO2, and that's because more CO2 pushes that equilibrium and that reaction forward. So that's kind of expected. And then when we look at the interaction between pH buffering capacity, CO2 and pH, so that last plot is now on the left, and we've now comparing that high pH buffering capacity with a low pH buffering capacity. And by far, pH buffering capacity has the much bigger effect. And so we can see much higher rates of CDI in all scenarios where the soils buffer or resist changes to pH less. And it's important to note that in these scenarios, this is our low pH buffering capacity scenario, but this is still more pH buffering than a lot of other models, or any other model has included so far. So you can see how easy it would be to overestimate CDR based on modelling results alone, if you don't include soil properties. And then If you looked closely at those previous results, you might have noticed that our CDR rates were actually higher than what could be explained just based on weathering alone. If we know the mineralogy of the materials, we can predict how much max CDR there is, and we're seeing more in these models. And so there is some CDR that we can expect due to other changes in the soil that adding the weathering material invokes. So the soil becomes more able to hold carbon. And I would love to go into more detail about exactly what changes are driving this pattern, but I'm currently dealing with this thing that I have to try to untangle, and these results only got ready last week to start looking at. So first port of call for future work is to explore and explain the remaining results from this work. We also want to run some longer model runs up to 100 years to kind of test the idea that cations held on the soil will eventually result in CDR down the track, even if not now. And then some kind of ideas that I would like to do in the future would be to improve the realism of the soil water parameters, integrate our geochemical model with organic carbon models, integrate our model with a crop productivity model like AppSim. And I think it's important that we strive to improve the user friendliness of the model because modelling is an important tool for monitoring, reporting and verification. No matter how cynical you are of modelling, we will need to use it because measurements in the field are really difficult and expensive, and we also, these processes are very slow, and so we can test a much wider range of properties using our modelling than we can just with field trials alone. So in conclusion, we found that the optimum soil pH for CDR by enhanced weathering is 6.5, but this depends a lot on soil properties. And that the effects of weathering on multiple interacting soil properties makes quantifying CDR just from weathering alone more difficult than expected. And we need to have a focus on continued development to increase realism and user friendliness of models for accurate monitoring, reporting and verification. And because I always feel like we need to point this out, that net carbon emissions will result if we roll out enhanced weathering on acidic soils because we see negligible CDR in these conditions. So we have to be cautious about that. And I just want to thank SRA for funding my project, and Peter Wade, Amy Lewis and Lila Taylor for help understanding and getting feedback on their models. So thank you.